The broadcast is now starting. All attendees are in listen-only mode.
Welcome to this evening's vBrownBag. This is Frank speaking, and today with me I have got Yves Fauser, who's going to present NSX for Kubernetes, advanced networking and security concepts. And just a little bit of housekeeping before we kick things off. If you have any questions during the webinar, I think if you're very happy to take them head on, right? People don't need to wait until the
that's the easiest way of doing it.
Yeah. So either raise your hand or post your questions in the chat, or you can also use the Twitter hashtag vBrownBag. We've got weekly shows going on. If you do want to present the topic yourself, feel free to reach out to me at fbuxel via Twitter, or simply use our website, www.vbrownbag.com. And with that, over to you, Yves.
Okay, so now you have to pass me the presenter rights, I guess. Yep. Go. Okay, so hello from my side also. My name is Yves Fauser. I'm a Senior Technical Product Manager in VMware's Network and Security Business Unit. And yeah, as Frank already said, I'll present on NSX for Kubernetes, and that includes obviously a lot of Kubernetes network topics. So standard disclaimer slide, I guess you saw that quite often already, so we'll just skip it. We'll start with a quick NSX-T introduction. Actually, it's funny that I have 2 times a 1 here, so sorry for that. Then we'll go into a Kubernetes networking overview, and then we'll see how those things tie together in the integration, followed by a demo, and then we can end the session with some more Q&A. Okay, so NSX-T. A lot of you guys know NSX for vSphere, which is our prime product for the vSphere world. So what is NSX-T? Well, it aligns to the vision we have already laid out 2 years ago, which is having NSX everywhere, having NSX in private and public cloud environments, on-premise, off-premise, for end users, for any kind of IoT devices, branch offices, and for new app frameworks. And with new app frameworks, what we're currently targeting the most is Kubernetes and Cloud Foundry. And so this session is especially about Kubernetes and NSX. And the platform we are using for all of those things is NSX-T. Simply because if you want to be able to support multiple hypervisors, if you want to be able to support multiple public clouds, private clouds, etc., you need something that is independent from vCenter and from it's decoupled from vCenter, and that's what NSX-T gives us. So NSX-T is composed of, first and foremost, the transport side, so the data path or the data plane. And here we're talking about kernel modules for ESXi and for KVM, or Linux OSs to be more specific. On ESXi, we are using the vSwitch that we also use for NSXV. So it's the VDS plus specific kernel modules that we have for NSX-T. On the KVM side, we're using OVS. Then we have other types of what we call transport nodes in the data plane. One is the so-called NSX Edge Gateway. So this is where we have layer 3 services and also other advanced services like NAT. This is our entry and exit point of the virtual networks to the physical network over a layer 3 hop, so over a routed hop. We're also supporting layer 2 bridging, where we can connect VLANs in the physical world to logical networks in the virtual world over layer 2. So we're bridging those two, and you have a direct layer 2 adjacency without going through a routing hop. Then we have the control plane side, which is the NSX controllers. It's a cluster of 3 nodes that share the load and that form a cluster for high availability. And that's part of this whole control plane, management plane separation. Then we have the NSX manager. This is your entry and exit, not exit, entry point to the configuration through the API, also the UI. In terms of Kubernetes, you will see it's the target endpoint for the API, which we create objects in NSX. So this is where you define what the logical networks should look like, and then they are persisted and then sent to the control plane to be actually done in the data plane. On the cloud consumption side, we have all sets of things. It can be OpenStack, it could be Kubernetes, it could be VRA in the future, VRO. So anything that can call the API is basically that consumption. And here we're talking about Kubernetes today. So one additional level of detail, which is the workflow. So if you make a configuration on the management plane node, the first thing that happens is that this configuration is persisted. So you would create a logical network, a logical router, and that is just first and foremost entered into the database and persisted. Then the NSX manager talks to the control plane side, to the NSX controllers, and informs them of a new object being created, something like a logical switch. And then the control plane is talking to what we call the local control plane on the transport nodes. And this is where then the configuration is translated into low-level objects of the data path. So as an example, in OVS, it would be open flow entries in OVS that form the actual switching data path. So this is how things get realized in NSX-T. I guess that is the most important slide to really understand what we will be talking about in the Kubernetes integration. And this talks about the routing infrastructure or the routing layers inside of NSX-T. And I want to draw your attention on the picture on the upper left side. So here you see we have 2 tiers of routing. We have so-called tier 0 routers and tier 1 routers. And those are, I would say, administrative constructs that are influenced by the way people build a multi-tenant network today. So you would have a aggregation layer, which would be your tier 0 router, and that is where an admin pre-creates something. So think of like the central router in some co-location where the co-location facility owner is basically aggregating all the tenants, which are in some racks, and is attaching the tenants' routers to this core router. And you see that kind of set up here in the logical space too. So the admin pre-creates that tier 0 router, and then the tenants all get a tier 1 router that gets attached to the tier 0 router. And a tenant could be an OpenStack tenant, a VRA tenant, or in our case, as you will see, a Kubernetes namespace, which is a Kubernetes tenancy construct. Now, if you know NSX for vSphere, you might think that the tier 1 is the distributed router and the tier 0 is a centralized router. That is not the case in NSX-T. All routing layers in NSX-T can be distributed or centralized dependent on if they use services or not. If you only use routing without any NAT, then both the tier 1 and the tier 0 will be distributed. Of course, if you want to exit and enter the logical network to the physical network, you still need some central place to do so. That central place is what we call the edge gateways. And those edge gateways are either physical form factors, so a software installed on a bare metal server, or VM form factor, so basically your edge gateway deployed as a VM. These edge gateways perform all the services like NAT, but they also give you interfaces to connect to the physical world. And we're using Intel's Data Path Development Kit, DPDK, to achieve very high performance. So here we're talking in the bare metal form factor of up to 40 gigabits per core, per CPU core. So not per edge gateway, per core. Well, and the last picture on the bottom just shows that we are using encapsulation, obviously, to build those logical network, those logical switches. This encapsulation is different from what we do with NSX for vSphere. We're using another encapsulation protocol, which is called Geneve here, which is currently a draft standard, close to be finalized. And the benefit that Geneve gives us is that we can put in more metadata of the traffic you transport into the Geneve tunnel headers. So you can add metadata like what happens on every hop, etc. And we're making use of that in several tools. And one of the tools that makes use of this additional header space is the TraceFlow tool that you will see later in the demo. Okay, with that, we'll leave NSX-T. This was the quickest overview you could get. We can certainly arrange a new session somewhere to go into a deep dive of NSX-T. Yep, there's a question.
Yeah, one quick question on since the audience here is lot of home labbers as well. With NSX-V, right? You if you have VMAC Advantage, for example, you get licenses for download. If you're a V expert, you get licenses for download. From a encapsulation point of view, NSX-V was never an issue in that regard. Even if you have a very simple switch, everything just works, right? Is there anything you should keep or pay attention to with NSX-T? Is it the same, just basically rack stack your Intel NUCs or Supermicros or HP microservers and everything just works, or is there some configuration needed on the actual networking side that people should be aware of?
No, so from the networking side, everything is pretty much the same. I mean, the encapsulation protocol doesn't really make a difference if you use VXLAN or Geneve. One thing that you need to be cautious about is the fact that NSX-T edge gateways use Intel's Data Path Development Kit, DPDK. And so they make use of various CPU functionality, like huge pages, like EAS offload, like what else? Let me think. What else is it? So there are a number of CPU features that are simply needed for DPDK to work. And so no matter if you use the VM form factor or even the physical factor, you might run into situations where your edge gateway will not boot, especially if you use AMD chips or if you use very old Intel CPUs. So everything that is like, I don't know, 3 years old or so is still fine. Everything that is older than that, you might run into issues. Now with the NUCs, that's like Core i5 as far as I remember. I think that should be okay. I never tried it out myself, but
so the most popular ones that start to take 32 gig of RAM are either an i5 or i7, 4th gen, 6th gen, or 7th gen. So 4th gen should be decent enough, I'd say.
I would hope. I mean, I don't know about the huge pages, but I would hope. Actually, that's a good point. At some point, I need to try it out. I have 3 NUCs in my shelf here, but I never tried it out yet. Okay. So I guess let's go on from here. So Kubernetes, yeah. Is there another one or?
Yes, one more question on that regard, okay. Especially on the NUCs. So with the NUCs, you had basically one onboard NIC, right? So you had to trick ESXi a bit, either with a USB adapter or Volume Lam has a script on how to migrate with only one NIC to a DV switch to actually get NSX-V working. Any challenges with only one NIC port for NSX-T as well?
Likely, yes. So there is a way to use only one NIC also with NSX-T, but it's not that much out of the box. You need to trick things a bit with some API calls to do the migration of your VM kernel, your VM case to the NSX-T logical switch. It works, but it's not a out-of-the-box easy solution.
Oh, cool. Sounds like
at
nice
some point somebody needs to play with that and document it.
Yeah. Okay, cool.
Okay, so let's go on with the Kubernetes networking overview. So I guess Michael gave you a lot of information about Kubernetes itself last week. So for those that didn't see it, I'll recommend you to watch the recording. So I'll not go into a deep dive of all the components. What we are integrating with is both on the Kubernetes API server side and on the nodes with the so-called CNI plugin that I will talk about later. So Kubernetes has one great thing, which is you can ask for callbacks for changes of objects in Kubernetes. So if you create an object like a namespace or a pod, then we can watch for events on that specific path in the object model. And then we get a callback, and we are doing that on the Kubernetes API server side. So we're watching for events, and then we create things. On the node side, obviously we need to patch those pods, those containers, into the logical networks. And there is a standard, a spec called CNI, Container Network Interface, that the component of Kubernetes that runs on the node, which is kubelet, calls. And then the CNI plugin does its work, and we are providing a CNI plugin for NSX-T. So the CNI plugin does its work and then patches the pods into the logical networks. We'll go into much more detail on that in the next couple of slides. So talking about the pods, here's something that you need to know to understand the whole concept. I'm pretty sure Michael also talked about it, but since it's very important on the networking side, I'll repeat it. So Kubernetes itself doesn't really schedule containers. It schedules what is called pods. And a pod is a collection of containers. And the idea behind it is if you follow really the rule of only having one process in each container, then you will need multiple containers to work with each other to provide a single functional unit. So the example I always give is if you have a web server listening here on port 80, serving a website, then this web server will write logs. Now those logs somehow need to be sent out either through syslog, or they need to be collected and aggregated and sent to some central logging place where you do analysis on them. And that is another process. So that's not the web server doing it itself, right? So if you would bundle everything in a container, you would need to start an init system in a container, which is a bad thing from a purist point of view. So what Kubernetes gives you is the ability to co-locate, let's say, those containers that form a single functional unit. And those containers then have a clear process separation, but they have access to the same file system resource and the same networking resource. So now your web server is writing his logs, and your logging process that runs in a different container is able to read the logs because it has access to the same file system resource, and then sends it out to a log aggregator. So from a networking and file system perspective, they're using the same resource on the Linux OS. They're using the same IP namespace, and they're using the same file system. On the process side, they are isolated. That obviously means that a pod can only live on a single node. So you can't have two containers of a pod on two different nodes, on two different hosts, let's say. I guess that's enough for the pod. And again, Kubernetes schedules pods, and those pods get IP addresses. And in Kubernetes, every pod needs to be able to reach every other pod in the cluster through its IP address directly. Then there is a dynamic DNS service called Core DNS. Before it was called Sky DNS, that is running in the cluster. And this is used to do service discovery. So let's say you have a web front end with a couple of pods serving that web front end, and that web front end wants to find its app service. It does that by querying DNS and getting then the answer from core DNS about the IP address to contact or the IP addresses to contact for this service. So you don't hard code IP addresses or those kind of things in Kubernetes pod. And that works together with the east-west load balancing solution in Kubernetes, which is the Kubernetes service. So the Kubernetes service itself is first and foremost a way of organizing pods that serve a service. So in that picture on the left, we have two pods that are my Redis slave pods. So those, as the name says, give me a Redis service. When I create a service in Kubernetes, I will say, find all those pods that have a specific label in its name. So if I create a service, I define the selector, and in the selector I say search for pods that have the label Redis. And then on the pods for Redis, or on the replication controller for Redis, I say label those pods with Redis. And so when I create the service, it will now know that all these pods that have the right labels belong to that service. And it will list the pod's IP addresses as endpoints of the service. So now when my web front end wants to find this Redis service, it will ask for redis slave.cluster.local, and then core DNS will respond and will give, and now that's the important distinction, in either a single IP address or it will return different IP addresses each time it's asked. Now, the second one, the different IP addresses, obviously it gives the direct endpoint IP address every time it's asked, is round robin DNS. That's usually not what you want to do, because then you have all kinds of DNS stale caches, etc. So people don't do that. What we are doing is we are giving the service what is called a cluster IP. So that's a virtual IP address. On that picture, you see it as 172.30.0.24. And that IP address is present on each and every node, but is only available inside of the node. So if the web front-end pod sends traffic, or first of all, does a DNS request, it gets that IP address, then it sends the traffic to that IP address, to that cluster IP. And then, as you will see in the next slide, IP tables takes care of removing that IP address, selecting one of the real endpoints, one of the real pods, and sending the traffic to it. Again, I have a separate slide to make that more colorful in the next slide. So that's all for east-west load balancing. So you get distributed east-west load balancing for free inside of Kubernetes with what is called Kube-Proxy, which is what is using IP tables here. For north-south, that's a different story. For north-south, so if you want to reach something inside of the cluster from the external side, you need to either use a so-called node port. I'll explain that in 2 slides from now. Or you use what is called an Ingress controller. And an Ingress controller is your load balancer that is exposed to the outside world to do the north-south load balancing. And I'll speak about the Ingress controller in a little while, so I don't need to detail that now. So here's the promised diagram of what Kube-Proxy does for east-west load balancing. So if my web pod wants to reach one of the Redis slave pods, it will send the traffic to the cluster IP address. In IP tables, that cluster IP address is then translated to one of the destination pods, and it can either be sent to one of the local pods if there is one pod on that specific node or to another node, right? So on the wire, so in between those nodes, you will never see that cluster IP. You will always only see the pod's IP addresses. Now, I talked about node port as a solution for north-south, for entry and exit point into the cluster. And what people use for node port is you configure some external load balancer. Think of your F5 load balancer, or maybe even an NSX load balancer or whatever. And that one hosts a virtual IP, which resolves if you do a DNS query from the external side and listens to TCP port 80. Then that load balancer is programmed to send the traffic from TCP port 80 to a pool of servers, which is all the nodes in your cluster, or maybe selected nodes in the cluster. But it sends the traffic to the nodes management IP addresses, and then some ephemeral port. Here I use the example 30123. That traffic then hits IP tables on TCP 30123, is then going into the same table we saw earlier for the load balancing to pods. The destination IP, which is the management IP of the node, is replaced with the real destination IP of one of the pods. And that might be one of the pods on another node, so it exits the node again and goes to the other one. So that's not a very nice way of doing things, especially your physical load balancer will have to be configured with a lot of static servers, and health checks, etc., can get complicated. So yeah, let's just keep it this way. It's kind of a hack. It's not really what we would want to use in a very dynamic environment. And that brings us to Ingress, which is what people mostly do today. And with Ingress, you create pods that serve quite often both the data path of the Ingress and the controller path. So those pods talk to the Kubernetes API. They watch for so-called Ingress resources, which are load balancing rules, pointing some host entry like bikeshop.com here in this picture, and maybe even some paths after the host, and points them to a destination service. And that destination service would be my web front end here. And then the data path side of the Ingress controller is programmed to get that traffic, to look for the host name and the URL, and to then send it to the destination pods. So it doesn't send it to the node's management IPs in the node port way as you saw before. It really sends it directly to the destination pod IPs. And as I said, mostly you have a combined data path and controller implementation, but there are some implementations out there, like the one from F5, where you have the controller actually programming an external load balancer to do the same job. So both is a valid way, and the Ingress object itself is really just a layer 7 load balancing rule. Okay, so this is one of the last slides on base concepts in Kubernetes, which is the namespace. I'm not sure if Michael talked about it. In Kubernetes, the namespace is both a name uniqueness construct as well as a tenancy construct. So it started as name uniqueness. If you have two Redis master pods in your system, then their name would collide. So there is no things like UUIDs in Kubernetes. So again, the name would collide. So you put a different prefix in the path, and this is called namespaces. But namespaces then were enhanced to be real tenancy constructs. It started off with quota per namespace with CPU and memory limits, but now we also have role-based access control on a namespace level, so you can define what user groups or users are allowed to do what in which namespaces. And we also have networking policies. So I can define on a per namespace basis what is allowed into the namespace and what the parts inside of the namespace are allowed to reach. Are they allowed to reach each other? So now it's a real tenancy construct. I would pause for a little second. If there are any questions, I would take them now.
No questions as of yet.
Okay.
Just double
So
check.
then I'll just.
Yep.
Okay, then I'll just go on. So in terms of topologies for base Kubernetes, let's say, without any additional network integration, what you get is what I call the flat routed topology. And with that, I mean there is no tenancy in that routing topology. And the way this works is, as I said, every pod in the Kubernetes cluster needs to be able to talk to every other pod over its IP address. And each IP address of the pod needs to be unique. So that's very different from Docker. If you know Docker, then you can install 10 Docker hosts and it will all use the same IP addresses on the Docker Zero bridge, right? But not in Kubernetes. In Kubernetes, every node needs to have a specific IP address range for the pods that are running on that node. So here, node 1 uses 10.24.1/24, so that's the first subnet, and here we have a 2. So if this pod wants to talk to another pod on another node, it needs to somehow exit that node and needs to be routed by either the physical network or whatever the underlying network is, which might also be an IS network, like could be NSX again. So the underlying network needs to know which subnet is on what node. And if you just use physical gear, then you have to enter static routes into each and every of those physical switches to point to the right node. And this is one of the biggest problems of this implementation, which is you need to somehow automate the route creation, or you need to accept the fact that you need to ask a network administrator to create those routes. Of course, in a lot of cases, this routing addition would be automated. On the positive side, you don't have any influences of NAT. You don't break any protocols with NAT. And if one of those pods talks to some external system, it's visible with its own IP address. But that IP address only tells the outside world it came from that Kubernetes node. It is not related to the tenancy construct. It's not related to the namespace or anything like that, which is kind of difficult in today's enterprise networks, because especially external firewalls or ACLs in database systems, etc., they want to match on some IP address and they want to know, does it come from this tenant or does it come from that tenant? This is difficult because you can't really distinguish between from looking at the IP address if it comes from one tenant or the other tenant. Now, with all these complications of having to add routes to the physical network, people started to use overlays between the nodes. And the most popular one is a technology, an open source project called Flannel. There are others. There is Weave, there is all sets of implementations. And here, instead of asking for routes on the downstream network, the nodes themselves learn from each other's subnets, or learn each other's subnet through a centralized key value store. In Kubernetes, they're using the same key value store that Kubernetes itself uses. And then they basically distribute the reachability information between all those nodes. So now if this pod here wants to talk to that pod, it will send the traffic out, and here the Flannel agent will now know to reach that destination IP, it needs to encapsulate the packet with another additional IP header, send it to the destination node where this additional IP header is removed, and then it's going to reach your destination pod. So it's the same as what NSX does between hypervisors, but here we're doing between Kubernetes nodes. So that solves the routing challenge. The problem with it is there are multiple problems with that. First of all, you need to somehow get in and out of those overlays. And to get out, you basically have to use SourceNet, and you use the source IP of the node itself as the source IP of the traffic from the pods. So now, if you look again at our external firewall or at our database system, it's not that it only now sees the pod's IP, it now only sees the node's IP with some ephemeral pod. So it gets even more difficult to actually find out where the traffic came from. And you need to open up a whole lot of range of nodes, IP addresses, and ephemeral pods that you allow access into some core pieces of your infrastructure. On the other side, to get into the overlays, you only have two possibilities, which is Ingress or node port, right? And for node port, it has the drawbacks that I said. So you need to have some external load balancer that points to either all your nodes or some selected nodes. You will have cross traffic between the nodes, etc. So it's not really ideal, but it solves the first challenge, which is not to have to program the physical layer. Okay, so now that I said what the base implementation is doing and what others are doing, let's have a look at what we are doing and how we do things differently. So the first thing that we decided was to give the tenancy construct in Kubernetes, which is the namespace, a network meaning. So we wanted the namespace to have specific IP subnets, specific routers and switches, and that's what we did. So if you create a namespace in Kubernetes, we will create a tenant router, a tier 1 router that I explained earlier. We will create a logical switch. We will start off with one logical switch, and we will address that logical switch with a subnet that we retrieve from NSX's new IPAM functionality. So now we really can distinguish if the traffic comes from that specific namespace, it will come from that specific subnet, or there is a little more of a detail from a specific SourceNet IP. Why am I saying that? So we had different sets of customers. We had customers that said, okay, I don't want those 10,000s of pods to all have a routable IP address in my corporate network. I don't have enough IP addresses to assign to pods. And so I want those pods to be behind NAT. I don't have a problem with NAT. And so the default way of working is if you create a namespace, we will assign a subnet to that namespace that will address those pods. But we will also create a SourceNet entry on the tier 0 so that if traffic comes from that namespace, it will use that specific SourceNet IP, which is also assigned by NSX. The big difference between what we are doing and what the SNAT is doing in the overlay case that we saw before is that this SNAT IP is specific to the namespace. So now I can enter that IP address in my firewall rules, in my database, etc., to be allowed to access backend systems. And that IP address is attached to that namespace as long as it exists.
And I would assume through the IPAM functionality, I actually have choice about what the exact IP range is going to be, right?
Correct. Yeah. Correct. So I create a block of IPs, and then a subnet is assigned from that block. And so I then see what block was assigned to that namespace. I can enter that in my firewall rule table.
Okay, cool.
Now, on the right side here, you see namespace bind uses a different set of IPs. And that's because we also support the case where somebody wants to create a namespace that doesn't use NAT, which might be because there might be protocols in there that break because of NAT, or because you really want to see each IP address that was assigned to a specific pod in logs in firewall systems, etc. And so what we are allowed to do is to create a namespace with a specific annotation saying, don't use NAT, no SNAT for that specific namespace. And then it will use a different IP block out of NSX's IPAM and use a different IP range and will not create that NAT entry. Then obviously here we have a high performance entry and exit point of this overlay network. So we are not using the management IPs of the node VMs themselves. We are really entering and exiting the networks through our high performance gateway that uses TPDK. Then here down on the downlink side, each and every of these pods is connected with an interface to a logical switch in NSX. And those logical switches span across all the nodes. So they are not really specific to the node, they're specific to the namespace. And for each and every of these pods, you have the full set of features that you also have for VM interfaces. We have all sets of counters. You can start mirroring sessions, so send traffic to an analysis station, export flow records and analyze all the flows that happen between pods. You have the troubleshooting tools, and we apply spoof guard to every pod. So we really enforce the IP address and MAC address that get allocated to that pod. And in fact, we have a report out there from Coldfire that tested our NSX-T Kubernetes integration and validated it that you can use it in a PCI context and put pods in one namespace and isolate it from other namespaces and have cardholder data in one namespace and any kind of other services in another namespace. So that really gives you a whole new set of possibilities to do real isolation inside of Kubernetes. Okay, what else here? Yeah, each interface has its firewall, just as NSX does, right? For VMs, it does that for pods also. And I guess I'll leave it with that. So the component that does all this magic and creates all those topologies, etc., is a piece of software we call the NSX container plugin. And that NSX container plugin is a Docker image that you will find on the download pages of NSX on downloads.vmware.com. So you would upload that to your private registry and then create a pod itself or a replication controller in Kubernetes that runs that piece of software for you. And on one side, it has an adapter layer where it talks to the Kubernetes API. Later on, we will see other implementations like Cloud Foundry, etc. But right now, we are talking about Kubernetes. And on the other side, it talks to NSX Manager over its API to create all those objects. And in the middle, we have kind of a workflow layer that does all the creation of objects. So let's go through one example. As I said, Kubernetes has this capability to watch for object changes. So this is what we do. When we start the NCP, we will watch a whole set of objects, and one of them will be namespace events. As soon as a user creates a new namespace, we get a notification, and then we start our workflow, create a logical switch, create a tier 1 router, request an IP subnet out of the block, and attach that logical switch to the logical router and a tier 1 logical router to the tier 0, and create the SNAT entry, right? So quite easy workflow. Here's how it looks like if you create the namespace in Kubernetes. Then, as I said, you create that topology. You create another one here. And what I want to show in this diagram is if we run out of IP address space in one of the namespaces because we have more pods than what our initial subnet can allocate IP addresses from, then we will create a second logical switch and add a subnet to the namespace And so the whole thing grows and shrinks dynamically. Here's the annotation that I talked about. So for a namespace where we don't want to use NAT, we can say no SNAT true. And if NCP sees that, it will not create that source NAT entry on the tier 0 so that you can use direct routing. Okay, let's talk about policy and firewalling. So we have two sets of capabilities. The first one is what I call predefined label-based rules. And so in this case, we can match on metadata that we see from Kubernetes. So if you create your Kubernetes pods or your Kubernetes constructs, you can label them and you can add arbitrary labels. And we copy those labels onto tags for the pods in NSX, and that can be statically matched into firewall rule sets. You will see that in the demo because I make use of that in the demo. So with that, you can define admin rules that are on top of any kind of rules that a developer might use in its namespace. So you can either predefine everything and have your users specify the right labels when they create their constructs, or you just use the admin rules for base policy, like I don't want this protocol to ever be allowed into or out of the namespaces. And then there is Kubernetes network policy, which is the policy language in Kubernetes itself, which is attached to the namespace. And here a user can create its own sets of policies where the user says, okay, this is what should be allowed into the namespace. This is where the traffic is allowed to come from. And in the next version, we will also have the ability to even define what goes out of the namespace. So pretty powerful tool that uses the Kubernetes language itself and the Kubernetes API. You unmuted yourself, so you likely had a question.
No, press the button by mistake.
Okay, good. So here's the predefined option. So here I'm tagging or I'm labeling my pods with a specific sec group equals web. And actually that's arbitrary. That could be any kind of label, right? We just called it sec group here because it kind of makes sense for us. And then based on these labels, we can match specific firewall rule sets. And that match is also across labels or globally in the system. So that's the more manual way of doing things. And the more automated or the more Kubernetes way of doing things is to use network policy. And here we define in the spec what is actually the destination. So in this case, it would be all pods that have the label app equals web. And then, okay, here I'm allowing from that specific namespace that is from the DB layer and then assign pod AD. I don't know how much sense this thing makes, but you get the point, right? So you define the policy in Kubernetes itself, and NCP will translate that for you and will create dynamic security groups that includes those pods, and that will then match on a specific TCP port as the destination. So it creates all the firewall rules for you. Okay, for east-west load balancing, I showed you IP tables before. I talked a lot about IP tables. Now for NSX, we're actually not using IP tables because we are pinning down the traffic from the pods through OVS to the downstream hypervisor vSwitch. And actually, I hope I didn't forget to add that slide, else I will have to explain it verbally. And since we're doing that, we needed to change the way we do the east-west load balancing in Kubernetes. And we're doing that through OVS flow entries or OVS load balancing entries. So we created a special version, let's say, of Kube-Proxy, which we call our NSX Kube-Proxy, that does the programming of OVS to implement this east-west load balancing. And with that, reducing some of the latency and having a clear separation between management traffic and pod traffic. For the Ingress, what we do is we validated the use of the Nginx controller, which is one of the most used Kubernetes ingresses. And we added some functionality that if somebody puts that Ingress controller into a namespace network, then we will automatically create a what I would call floating IP, so a source NAT and DNAT pair out of our external IP addresses, so that the data path itself of that Ingress controller stays in the namespace network, so in the isolated network. But to make it reachable from the outside world, we assign a netted IP address that is added to the tier 0 router so that you can reach your Ingress controller. Yeah, and here you see that we can use all the troubleshooting tools that we also know from NSX for virtual machines, also in the case of Kubernetes. And I definitely forgot to add the slide where I talk about multiplexing the pods traffic to the VNIC of the node. So what I would do is I would show you the demo, and then I would try to find that slide and quickly insert it, because I think it's important to clarify that. So, but let's go to the demo first. Go ahead.
And otherwise, we're going to see your extremely well-defined whiteboard skills in what's the equivalent of MS Paint on macOS?
I don't know. No, I will not do that. So let's do the demo first, and then I'll search on the files. Actually, let's do it otherwise. Let's just open up this one here. Let's take that one. That's actually good. That's my VMworld session. And then let's open up the right slide. Here we go. Just need to be flexible. So yeah, that's what I wanted to talk about, which is the way we are pinning down the pod traffic to the hypervisor vSwitch. So one of the drawbacks of using overlay encapsulation directly from the node VM is that if you, like in the flannel case we saw before, is that if you use an overlay networking solution already on your hypervisor layer, then you end up with a double encapsulation problem. So your node VM is encapsulating the traffic in an overlay and is having to chop this traffic into 1500 bytes packets. And then your downstream hypervisor does the same and then encapsulates it again. So you're losing a lot of the benefits of acceleration technologies that we have in the hypervisor vSwitch layer. So we didn't want to lose that, and we didn't want to complicate things by having each node being a transport node itself. So each node VM being a transport node itself. And to solve that, we had to find a way to identify the traffic coming from specific pods in the hypervisor vSwitch, even so the pods are running in the VMs themselves. And we do that by the help of VLAN IDs. And those VLAN IDs are specific to the node, or even specific to the node's VNIC. So as you see here, that pod is pinned down to the hypervisor vSwitch on a sub-interface that matches VLAN ID 10 and the IP and MAC address of the pod. And for that pod, we use VLAN 11 to identify another logical port. And we reuse those VLAN IDs on the other nodes. So they are the VLAN IDs are unique per node. So with that, we still have enough ID space to run 4,000 something pods per node. And today, one of those nodes usually doesn't run more than 110 pods. So we are far away from having a scalability limitation just because of using VLANs here. And all that logic of creating those pipes, as I would call them, is done through our NSX CNI plugin and node agent running on those nodes. So when kubelet creates that pod in Kubernetes, it will call that CNI plugin, and the CNI plugin will inform our node agent, and the node agent will create those interfaces in OVS and attach the VLAN ID to that interface so that when the traffic comes from that pod, it's pinned down onto the to the logical interface on the hypervisor vSwitch. That green bow here is supposed to show you that if this pod needs to talk to that pod, there is no direct communication. It always goes to the hypervisor and back. And on the hypervisor, we enforce firewall rules, spoof guard, etc., to make sure that nobody is spoofing traffic or is trying to bypass rules by taking ownership of the node itself. And with that, we also create a clear separation between management traffic and traffic that comes from the pods themselves, so of payload traffic, let's say. Okay, and with that, I'll go to the demo now. Let's first log into NSX here. 4 minutes, I can do it. I can do it.
We are not time constrained.
Okay, so what you see here is my vSphere environment, and as you can see, it's nested. So actually, all those hypervisors here run as nested hypervisors, nested EXXI on a relatively beefy server. So if you want to play with the stuff, that's a good solution, right? Put yourself a nice server in the cellar, and then use nested hypervisors.
Well, from a resource perspective, what have you configured? 16 gigs of RAM per nested ESXi?
Yeah, that's pretty much it. Yeah, 16 gigs.
So that's 32 for the nested Kubernetes. How much would you need for roughly for the outer NSX-T deployment that you have to give people?
Should be okay with 30-ish.
So with about 64 to 96 gigs RAM, you're kind of good to deploy a full lab on this on your own if you get the bits through the expert program or something similar.
Exactly.
Oh, cool.
Okay, so what you see here is I have my Kubernetes master and 2 nodes. The nodes, as you see, are patched into a logical switch of NSX, node vivs. So this is my transport connection or my payload connection. And then here, my VLAN 41 is just my management interface, right? And that's the same for the master and the 2 nodes. Now take note of that Redis DB server. That's simply a database or a Redis that is running on as a VM, and is also attached to an NSX-T logical switch with database VMs. And in the demo, I'm showing the combination of having an application that is having the database as a VM, but the Kubernetes pods running inside of those nodes as pods, as containers. So let's look at what is already present on this logical switch side. Here's the database VM. Logical switch, and if you look at the ports, you see here's my Redis database VM. You can look at the VIF, we see the VM name, and so that shows you that NSX is also able to import those details from the VMs and match on them. You will see that later on. Now, here you see a number of logical switches, Kubernetes cluster 1 default, kube public, kube system, and those are from the existing namespaces that we have in Kubernetes. So when you install Kubernetes, you will automatically get default kube public and kube system as namespaces. And when you start NCP, it's going to create the logical switches for that automatically for you. So now we'll create a new namespace called Yelp app. And as soon as we do that, you can refresh here, and then there will be a new logical switch created called Yelp app. And right now it only has 1 port, which is the logical router. So also on the routing side, there is a logical router called Yelp app. And if I look at its router ports, we have an IP address and a subnet assigned to it. As I said, that comes from NSX's IPAM solution. So here we have a block, an IP block. That IP block serves IP addresses out of that big pool of IP addresses. And here in the subnets, you see we just used this newly created subnet. So NSX requested a subnet, got it from NCP requested a subnet, got it from NSX Manager, and then addressed the tier 1 router with the right IP address. Okay, let's go back to the switches. And now the first thing I'll do is I set my context to use that newly created namespace on the CLI. So now everything I create will be created in that namespace. And here I'm now pointing Kubernetes to get my my definition of what should be created from an HTTP link, which points to GitHub. So if you look at GitHub here, I have the spec of that application in the VMworld 2017 demo repo. So the first part is my web front-end spec. And here I'm creating one replica of a pod that that uses this container image here, Yelp UI mrefere, which is simply on the Docker Hub. And here I attach my labels, and one of the labels is subgroup web tier, and we saw that in the presentation before. So that's my web front end. And then here we have my app layer, so the app server. That takes it from the Docker Hub again, but this time from my org because I changed it a bit for this demo. And here the subgroup is again app tier. And here's the port that it uses. Now here we come to the Kubernetes services that glue together the app server and the web front end. And then finally we have our Ingress rule, which says, okay, expose that Yelp UI service on that host name yelp.demo.eve.local. That's basically what we create here. So we'll shoot that, and now it creates those objects. And now we can wait here for the pods to be flipping from the container creation to the running phase. First one is already running. Second run is running. And then if we look at the details, you see the sec group here that got attached, or that is the label. If we look at the ingresses, then we see, okay, this is the host name that we can access our application on. So before we access the application, let's have a look at NSX, what got created. So we still have the ports in down. They will flip to up in a second. Let's try that later on again. So one of them is the Yelp UI. I want to try it. Oh, it's still down. Okay. And the Yelp UI, you see down here, has all the metadata from Kubernetes on the port for the Yelp UI. And one of the metadata is the label that we just saw in my definition. We bind a specific IP address that we enforce and a specific MAC address that we enforce for SpoofGuard. And if we look, we have all the counters counting up. We have all the features like port mirroring, etc. here. So all the stuff you get from a logical port, we also, for VMs, we also have for our Kubernetes pods. Oh, come on, flip up. Okay, now they're up. That will be the same for the app server. Now, here I have dynamic groups, so-called NS groups. And those NS groups match on specific membership criteria. Let's have a look at the database VM criteria. Here, we're mapping on the VM name. So you saw before that I retrieved the VM name from vSphere, and that now means that I will match that logical port of that VM. So I can refer to all the VMs matching with that name is the database VM group. The web tier has a different membership criteria, which is if the logical port scope, which is the key, is set group, and the tag, which is the value, is web tier, then this is a member of that group, and you see the Yelp UI here. And same for the app tier. Okay. And then in the firewall, we basically have our admin section, as I said, and that admin section creates or defines what is allowed, what is not allowed. So web servers to web servers should not talk, so drop that. Web servers to app servers, yes, allowed to talk on that app port, which is 4567. App tier to database, yeah, is allowed to talk, and then DNS is allowed, and all the other stuff drop. So if we now look at our app, it should hopefully load. And here now I can vote for my favorite restaurants, and then it's counting up down here. So that data here is in the Redis database. So now we can break the application. What is always great for applications if we basically remove the database access, right? Applications love that. If I now refresh, then you will see, yeah, I can't vote anymore, and you don't see my my results anymore. And so
I think you should call tech support, definitely. Must be.
Yeah. And that's a good one. So what would tech support do? Well, they would use Traceflow. So they would say, hey, where could the problem be? Let's select the logical port of our app server, because no, it looks like it's something with the database access, right? And then as the destination, we'll take our Redis DB here, and we won't send a ping, we send real TCP traffic, and we want to see what is wrong with 6379, which is my Redis, 79, come on, which is my Redis port. So now I'm sending an artificial traffic into the system. So it simulates the traffic inside of NSX, and it goes from hop to hop and adds metadata to the Geneva encapsulation, as I said. And so now you get all the details, what happens on each of those hubs and what their state is. And here I see, yeah, well, actually we're dropping by firewall rule 2064. So now tech support knows what to do. We're looking at 2064. Yeah, somebody has changed that to drop. No wonder that the application is broken, right? And refresh. Just prepared it. Okay. So yeah, that was a demo. And in conclusion, because we're already over time, what are we doing with NSX? First of all, we are unifying the VM to pod networking. We are allowing micro-segmentation between pods in and out of those namespace networks. We enhance visibility, and I would say we make it easier to integrate Kubernetes into an existing enterprise networks with existing ways of how to create how to enable security inside of your data center. And with that, if there are any last questions, I would take them now.
So from my side, is there any type of hands-on lab available to toy around with this? Not everybody is as fortunate to have servers in their basement. There is a critical acceptance factor of the wife sometimes, right?
Exactly.
Both in noise, power cost, and procurement cost sometimes.
Yeah. So yeah, there was a lab or an HOL at VMworld, and it's certainly going to be made available to the outside world. I checked like 2 weeks ago and didn't find it yet. So I'm not sure when the HOLs of VMworld 2017 will be published, but I guess it will be published, right? Now that one is still using a little older version than the one you just saw here in the demo. And we're going to work on updating that HOL vpod also in the next couple of weeks.
Yeah, perfect.
Else, if you are inside of VMware, just ping me and I'll give you the right vpod name to start it.
Yeah, because I think, let me just grab your presenter rights real quick. And you can confirm that in a second. That this up here is the pod you're talking about.
I would love to see it. Oh, now I see it. Yes, it is.
Yeah, so that's available today. Perfect.
So when was it published?
I have no idea.
Okay, good.
But apparently within the last 2 weeks, I'd say. So yeah. Even if you're not blessed with an overabundance of hardware and just quickly want to deploy and play around with it, especially from a networking side, there's quite a bit of concepts to try and understand. The VMware hands-on labs are essentially a free resource. The good thing is you do not have to follow the lab manuals at all. So it's really a nice way to break an environment that you don't own.
Yeah, exactly. There are also NSX-T base labs to get started with NSX-T, which are also a very good resource to get the base concepts.
Yeah. Cool. Then I have one last remark, because Michael has been on the last couple of brownbags. He also contributed something here. This is Michael's blog, embano1.github.io. And just reading through the last couple of posts, if you are into Kubernetes stuff, I highly suggest to give this one a read. It is extremely deep dive content on there. And with that, I would keep the line open for 2-3 more minutes. If there is any further questions, either post them into the Q&A or into the chat, and I will relay them onto Yves. And with that, also thank you very much for presenting, Yves. It was great having you. I think this is one of the brown bags that I'm gonna rewatch the recording 2 or 3 times just to wrap my head around the whole networking stuff.
Yeah, it's a lot of content. Yeah, it's a heavy brain dump. I agree.
But that's what makes a cloud interesting, right? Compute and memory are pretty boring.
Exactly.
It doesn't look like we have any more questions. I think everybody's brain is just smoking with the information you've given.
Good.
Again, if you want to get involved, if you want to do more sessions on vBrownBag, Yves, you're very, very welcome. Let myself know. I'm easily reachable via Twitter. My phone never stops. And
okay.
We can set something up either still in this year, we still have 4 open slots, or next year as well. With that, thank you very much, and have a great evening, day, or afternoon, everybody.
Okay. Bye, guys.
Thank you. Bye-bye.